So the topic is flow-aware real-time SDN analytics. So quick overview in the agenda. Look at flow-aware networking is a popular concept, but we'll see what is really practical with flow-aware networking. Then look at some few interesting analytics applications. Then how these can be integrated into OpenDaylight, and a quick summary. So first, what is everyone must be quite familiar with this, but it kind of this gives a nice overview of the different types of flows in the network today. On the left side, you have the short-lived flows. One is a large flows, which are search applications, and the short-lived small flows, chat or short-form video content, video clips, etc. Then on the right side, you have the long-lived flows, where two categories: long-lived large flows, like file transfers, tunnels, or Hadoop shuffle phase, large file exchanges. Then you have the long-lived small flows, essentially video content, which lasts for a long time but low bandwidth, like catch-up episodes, movies. So our focus is going to be on the top right quadrant. Here are the key reasons that the long-lived large flows are indeed the ones which are observable in the network, and also hence controllable, and also scalable in the sense from a table size perspective. Whereas if you look at long-lived small flows, they're definitely observable and controllable, but not necessarily scalable from a table size perspective, networking devices. And just focusing on the long-lived large flows is key to real-time SDN analytics, as we'll see with interesting use cases. So just to give a landscape today, yes, flow-aware networking has been implemented, but some of the very interesting issues today which exist with NetFlow or current versions of IPFix are essentially around trying to learn all the flows, short-lived, long-lived, all the flows, and then later filter them, right? So the issues with such an approach is essentially your flow cache size, because you're trying to learn all the flows, and whereas indeed the short-lived flows are a vanishing act. So you learn them and then purge them. So you need a huge flow table size, and also the fact that because you're busy learning all the flows, your CPU utilization on your router will spike up. So these are the key problems in the current flow-aware networking approaches. So moving on now, focusing on long-lived large flows, we'll talk about interesting ways to do automatic recognition in real time. So broadly, there are two techniques. One is based on sampling technologies, and other is inline line rate techniques. And the key parameters for these are essentially the programmable parameters in these implementations. The first one is the observation interval. This is the minimum amount of time you need to observe a flow before declaring a flow a long-lived flow. The next one is the minimum bandwidth threshold, as you can see here. That is the minimum bandwidth of a flow above which you declare the flow a large flow. So these constitute the definition of a long-lived large flow. And now moving on to sampling technologies, what happens is these are really lightweight on the router, because you're just, after all, sampling 1 in 2,000 or 1 in 10,000, right? And indeed the recognition of these long-lived large flows happens in an external device. For example, SFlow-RT is a popular one where you can do real-time recognition. And here, in this case, the programmable parameters would be along the lines of, for example, if you want to reduce FTP traffic, it would be around 2 seconds observation interval, and then the minimum bandwidth threshold would be roughly 10% of link bandwidth. And now, what is very interesting is such sampling technologies are very amenable for long-lived large flow detection, because naturally sampling itself favors the big flows, right? It will automatically omit the small flows. And now moving on to inline line rate techniques. Here, some of the interesting advantages are about faster detection, right? And that means you're observing each and every packet and making a decision, not sampling. And studies have shown clearly that by observing each and every packet, you can make a much faster decision in learning about long-lived large flows. But again, here, the focus would not be on learning all the flows, but use small techniques like Bloom filters and all those to recognize them in real time, but learn only the long-lived large flows with minimal false positives. Here, what we are looking at is, for similar type of workflows like FTP, the observation interval could really be shrinking to, by an order of magnitude from 2 seconds to 200 milliseconds, again, because you're observing each and every packet. And the same bandwidth threshold rules apply, essentially 10% of link bandwidth, so that you go back and obey those properties of observability, controllability, and scalability. And indeed, the inline line rate techniques, this are being standardized in firm in terms of IEs, information elements, and the IPFix working group, specifically the observation interval and the minimum bandwidth threshold. So the challenge is, okay, now inline line rate techniques are interesting, but if you want to implement them in ASICs, it takes time, right? Basically, you have to rev up ASICs to implement this. So now here comes an interesting angle where you could use virtual switches and routers, software-based, to implement such techniques, where you avoid that going through a ASIC churn and all those, right? So much easier way of getting them to such features to market, but add value. So you can think of here, NFV really playing a role, software switches, virtual switches and routers, adding value to SDN. And also want to highlight that besides all these automatic recognition techniques, there are other methods. For example, the end user application may notify about the long-lived large flow and ask the network to do something. For example, in the case of scheduled backups. And also, all these are captured in detail in the following INTF working group draft. If you get a chance, please take a look. And this work is progressing very well in IETF. And now, moving on with this foundation, so we'll establish essentially a framework for FRSA, where we realize that performance and scalability is critical, and we need reaction time in the order of seconds. And we'll focus on analytics applications around long-lived large flows. Further in the presentation, we'll just call them large flows for simplicity, and use efficient automatic recognition techniques, sampling or inline line rate. And also, another very key element for the use cases we'll see is essentially using a hybrid SDN model, using the OpenFlow hybrid. So why this is important is we want essentially the same port to handle OpenFlow rules and traditional packet forwarding, right? So in essence, when you're adding a new rule, we just add maybe a QoS policy, but let forwarding happen today. That means such interesting use cases can be deployed in today's networks as is without any changes to forwarding behavior. And that is one of the key points to note. And also additionally, besides decoupling forwarding from external policy, the additional value is this is scalable, and and existing flows are completely handled by today's control plane mechanisms, and only exceptions use really the OpenFlow. And also, in case the controller fails, it's very robust. You can keep forwarding; nothing is going to happen because you adding some QoS policies or other kinds through the SDN application and controller. And the hybrid SDN model, I mean, we have hybrid open flow, which is in production and can be used. And also this work is being pursued in IETF I2RS, same hybrid SDN model, but where you're touching the rib and not the fib, like open flow. And now let's look at some interesting use cases around FRSA. The first is a popular favorite topic, DDoS, and let's see how we can accomplish layer 2-4 DDoS detection mitigation real time with this. So if you look at the landscape today on DDoS attack detection and mitigation, for layer 2 to 7, any types of DDoS attacks, you need a dedicated, expensive hardware appliance. That's the present mode of operation. And switches and routers, you can have static rules, saying that, hey, these are the static policies, I want to forward traffic, what traffic goes through my firewall or not, but that's pretty much it, right? And the static rules are not scalable and operationally not easy to manage. And that's the current story. Let's see. So now, with the framework we established, something interesting is possible. So the key observation here is, what is a DDoS attack indeed? I mean, from a layer 2-4 perspective, right? Because switches and routers can handle only layer 2-4 and not layer 7, focusing on that. It's indeed, in fact, a large flow, right? There is a burst of traffic, there's a large flow, which lasts for some number of seconds, maybe a minute or 2 minutes, right? Or it could be more. And some of the favorite ones which are happening today are the UDP flood category, like DNS, SNMP, NTP. And in fact, I think the NTP is now kind of a NANOC favorite now, one of the mailing lists. And so basically, there's a large flow which can be detected and addressed right in the network. And you don't need to go to an appliance to accomplish this. And also, besides these UDP type of flood attacks, other popular ones which can be handled well are just the classic large flow IP5 tuple. For example, you have P2P traffic and it's kind of exceeding its bandwidth. You can have a policy to automatically detect and then enforce some QoS actions. And again here, the OpenFlow hybrid mode is key, where you can impose some QoS actions independent of forwarding. So now, tying all this together, how does it look? The first step is essentially, in switches and routers, you have sampling, S-flow sampling happening, and then the sampled S-flow goes to an external collector running S-flow RT, which performs automatic large flow recognition, which is indeed UDP flood or something like that, right? And also another important point to remember is, when you're talking about a flow definition, it's flexible in any field in the packet, just to set the baseline. It's not just about the IP5 tuple. It can be any set of fields which can be observed by a networking device. And so the next step is to convey the large flow to the DDoS SDN application, which would impose the relevant QoS action, rate limit, remark, whatever is not, based on the policy to the large flow, and then pushes the flow to an SDN controller. It could be OpenDaylight. And then that flow gets installed as an open flow rule in switches and routers, which would trap the DDoS attack, and with a QoS action, which could be drop, remark, anything. So this is kind of the life cycle of this and how all this happens in real time. And typically with S-flow RT, I think we have some published numbers. The large flow around 10% of link bandwidth, say on a 10 gig link, approximately around 4 or 5 seconds, the large flow can be detected. And if it's 20%, probably 2 gig, then you can detect it around a couple of seconds. Right? Well published numbers. So that is in this whole, real time SDN. Sure.
The flow that you're talking about consists of multiple flows, essentially multiple 5 people in this case.
So I think the best way to view it is it's an aggregate large flow. So for example, there's a destination IP address, right? Yes. So that's why I just clarified the definition of flow, where it can be any set of fields in the packet. It's not necessarily the classic IP file table. It's basically an aggregate flow. So, so this is kind of the whole framework and happening in real time, where the S-flow RT is playing a critical role in recognizing the large flow in real time. And of course, OpenFlow provides a high performance interface, and hybrid OpenFlow in switches and routers provides the capability to decouple QoS from forwarding. Right? That's the summary here. And this work is also happening in IETF and I2RS, again around the hybrid SDN model which I talked about. So potential deployments where you have seen a lot of interest in this idea is especially DDoS incidents are really on the increase in the internet, and especially in public cloud data centers. And you can read more in the reference, and Rackspace is subject to a huge DDoS attack which brought it down for several hours. And here the biggest benefit this solution can offer is it can complement layer 2.7 DDoS appliances and enable a tiered pricing model for the operators. So this is a service provider DC story. And not just that, we have also seen interest in research and education networks, where such tools and solutions can complement the existing layer 2.7 DDoS appliances.
How do you compare this approach with a BGP flow spec?
So the BGP flow spec, it's just a protocol. Oh, okay. So the question is how do you compare this approach with the BGP flow spec approach? So BGP flow spec, all that it provides is a communication protocol for conveying flow information, right? For example, if there is an attack detected, then you can use BGP flow spec to communicate to downstream. Basically, that's what it is, right? It's not about a framework for detecting attacks and then mitigating it. That's not BGP flow spec. It's just a communication model, right? So for example, in
Not the detection, but the rest of the, seems to me that the rest of the architecture you described there could be achieved also with BGP.
So basically, you're saying instead of open flow, you could, that is possible, that's possible. So yeah, totally. So in our case, we wanted to be kind of keep it more flexible with open flow, right, tied to hybrid open flow. That's the direction. That's why we would prefer this approach. And more reaction, once you've detected and all the switches support hybrid open flow, it's very easy to make it happen. And of course, wherever there isn't, we can do BGP flow spec for sure. So the next use case, interesting use case, is around local load balancing on lag groups. So here, if you look at the present mode of operation, what is happening today is lag hashing in switches and routers is unaware of the flow category. It doesn't know differentiate between the type of flows. It treats all flows as equal. This fundamentally leads to suboptimal lag bandwidth utilization, and where a large flow can penalize other large flows or small flows. This is the current problem today. So now let's see how we can solve this. So essentially here the key area is around how do you optimize in such a situation where bandwidth utilization is poor. So the sequence of events would be here the routers use S-flow sampling, and then the first step is an external collector. You recognize the large flows, right? And then you communicate that large flow to an SDN application, load balancing SDN application, which performs this set of steps. Essentially, the first step is the load balancing application would do is, hey, indeed, is there a problem to solve in the sense, so there could be an imbalance in the lag, but is there really an imbalance happening right now, correct? Or is it affecting my overall bandwidth utilization, right? So if there could be imbalance, but if there's no, basically one link is not, or few links are not peaking in bandwidth, then there's nothing to do, right? So essentially that means the first step is identify the congested egress member ports for lag. And now essentially what it comes to is, it comes to a strategy around bin packing for maximal bandwidth utilization. And the various strategies are around, first is alternative placement of large flows, where instead of just letting the large flow go as is, you're moving the large flow to a specific port using ACL PBR rules. And you could potentially, based on policies, reduce the priority of large flows, QoS actions. And also the other interesting part is, while you have adjusted the large flow to take a specific path, so now there are other flows which are going, right, all the other flow categories. So now we can essentially adjust the lag hash table to achieve the best redistribution of the small flows. So you're essentially, instead of today's model is the lag table is kind of kept symmetric. Basically, you have equal port distribution between all the ports. Instead, you will be giving lesser weight to the ports where large flows are steered. That's the key idea there. So with these bin packing strategies, what you've achieved is the maximal bandwidth utilization for the lag. And so the other interesting way of implementing this is, you could consider, because it's lag and completely local, you could consider implementing this as a collapse function in the router embedded application. So the biggest differences are, the reason you could probably do it is if you're using inline line rate recognition techniques, which you talked about before, then it makes sense to kind of embed it. But if you're using kind of an external collector approach, it's more prudent and smart to use the SDN approach. The rationale is, hey, you have SFlow capabilities in all these switches or sampling capabilities, then you develop this application once and you can leverage this across multiple products and platforms. That's the biggest benefit in this as an SDN application. And talking to our customers, they see value in both the approaches. And essentially, if you want to deliver value through ASICs and those kind of approaches, then go with the embedded application. But otherwise, the SDN application is the preferred approach. And this work is captured in detail in the IETF Ops Working Group in large flow load balancing.
How do you adjust the hash table?
So that would be a vendor specific call. Yeah. So basically, we will talk about the end of it, the vendor specific, correct? So that's why in each of the boxes you see the open flow and vendor specific, and even the open flow group table will also be adjusted. That's also part of the vendor specific right now. Yeah. Go ahead, please.
So in both of your use cases, large flow recognition is both of the use cases use the load balancing without AC. So you have a offline collector that is able to detect large flows. How feasible do you think it is to not have false positives and detect the large flow and to detect the fact that this is an EOS versus
So interesting question. So I think definitely that's all about the implementation, how you accomplish those. There are various interesting ways of doing that, and that's the whole IP around, how you specifically zoom in on the large flows and avoid the false positives. That's the key differentiator with SFlow RT or the kind of the inline line rate techniques. Unfortunately, there's some IP, so I can't disclose details.
Just fundamentally, you think that it's feasible
Exactly. So just to give you some hints along the direction. So the first is when you're using S flow. So you are naturally favoring large flows. I mean, you're ignoring the small flows, right? In the samples. And also then it comes to a problem of if you go back to analog theory, basically filtering the noise, and the noise is small flows, and just focusing on the large flows. And regarding the inline line rate techniques, something to think along is around counting Bloom filters, and having multiple hash tables. Those are some things to think about, where you just filter these large flows, but with a minimal false positives, and you quickly converge on them. And again, because you're focused on long-lived large flows, it's really scalable. You're looking at only a small table size.
You're proposing that this being offline, number of resources were dedicated to the Bloom filter itself, huge compared to putting it right in the cloud itself.
No, so the Bloom filter I was alluding to more like an inline hardware implementation, right? So I gave both the examples. So either way, you can make it really scale, because at the end of it, if you're looking at flows about 10% of link bandwidth, there are not going to be too many flows, right? And also fundamentally, by the definition of long-lived, studies have shown that inside a data center, when you're focusing on long-lived flows, you're looking at flows which at least last for 10 seconds. And in our case, talking to customers, we see of the order of more of minutes at least. Those are the types of flows we're focusing on. And if it's going to last a few seconds, we just don't care, because we can't do anything with them anyway.
So my question was more on that. What is the latency you see by the time you take this?
So I think the biggest challenge we have seen is, all these control interfaces, you want to kind of keep them optimal, right? For example, OpenFlow is definitely high performance. So you don't want to use some CLI or some mechanism. That's the reason for using hybrid OpenFlow. And likewise, each of these interfaces, we will strive to be optimal, right? So SFlow itself, we look at it, it's constantly pushing traffic inside samples and also counters. Is very efficient. And so in some cases, as you see, I've depicted this model as kind of a REST call to depict an open model where the application is not necessarily embedded in the controller, but it's totally, absolutely possible, as we talk about OpenDaylight, to embed this to make it more efficient. So the goal is keep all these interfaces high performance and very efficient. And then comes the, okay, how do you recognize the large flows very efficiently? That's where the problem comes. And also here, among the strategies for load balancing, just to give you some idea of what all to think about, when you do this, you have to consider a combination of best fit, first fit, and random fit. The reason I'm saying random fit is often we have seen in many deployments, the lag could be 64 port lag, or even 128 port lag. So in all these cases, just running through for a free slot may not be the optimal approach. Right? Yes, you can achieve the maximum bandwidth utilization, but you want fast algorithm convergence and reaction. So in that case, what you would do is, you'd have a set of bins where you are going through and then pick a random fit within them, various strategies. But yeah, that's a summary of how to handle this whole real-time SDN story. That's correct. Yeah. And also, operationally, there are some interesting trade-offs you need to make whenever you're switching a flow, especially a large flow. You may encounter some packet reordering, and especially if it's TCP, then what may happen is if there are 3 back-to-back out-of-order packets, then you could get some duplicate acts. So we have captured this also in IETF trap, and these seem to be trade-off well accepted by operators. Yes, it's not a free lunch, there is a trade-off. And also you have to remember that even in the case where we're adjusting a hash table, there could be some slight reordering. So all trade-offs for bin packing. Excellent. So potential deployments, we have seen a lot of interest. One second. So there we have seen in transit networks and internet exchange, especially in WAN, where you have IPsec tunnels and large file transfers. So it seems like 10 gig lag is a very common use case, and there is a very slow transition to 100 gig. Right? It's very slow, and there this can deliver substantial WAN bandwidth savings. And in fact, IETF, if you do see, there is a composite link work in that direction. In fact, bundling your 10 gig and 100 gig to ease the transition. Please.
So in your earlier slide, I mean, the flow definition here is 5 to 1.
Typically, that's correct. Yeah, typically, but not necessarily. So basically, when you're covering IPsec tunnels, right, you have to keep the definition flexible. Correct. It's not necessarily the inner flow, but the tunnel itself, right? Correct. So again, I think the best way to treat is keep the flow definition flexible.
Kind of, if you do it from aggregate way, you kind of do some traffic engineering between the. I think that's what you're trying to do. If you make it flow specific, yeah, I mean, two sets of flows from same source to destination having different fields. Both are sending the large flow. You probably distribute it among different links. And if you try to aggregate it and put it on the same link, it may not work that way.
Right, and so in the case of lag, so think about this in a core network where there are flows from different sources to destination, not all from the same source. Correct.
If you have an IPsec.
Yeah. So next one, global load balancing. Interesting. So I think from an open flow, many people maybe you've seen this use case, but I'll go ahead and point out something, how we are taking it to the next level. So if you look at today's hash-based ECMP schemes, so so I've drawn out fat tree topology in a data center. So what happens is you have two sources and destinations, completely independent, S1, D1, S2, D2, no intersection, right? And when they have large flows, what happens is in the core, you could have collision, right? And poor bandwidth utilization and poor application performance, all because the hash-based ECMP is, not flow aware. All that it knows is basically, it treats all the flows uniform, right? That's the fundamental problem. In essence, you finally land up with suboptimal network bandwidth utilization or poor application performance. So now what do we do? So the solution is large flow global load balancing, right? So here again, this is kind of interestingly very similar to the one we talked about, right? I mean the lag one, but now instead of doing a local bin packing, think of yourself as doing a global bin packing across multiple network nodes, right? So to summarize again, the first step would be suppose you take the S flow approach, right, sampling approach. The external S flow RT would be doing the large flow recognition, and then feeding to the global load balancing application, right, which would essentially identify congested links in all network nodes, not just a single network node, right. And here this would do globally optimal placement of large flows. I mean typically epifightable by adding a hop by hop PBR rule. So you'll add a PBR rule in each node to steer. For example, it's added here to basically steer the large flow across specific set of nodes. And also the other aspect is, I mean the interesting aspect I think which would have not been discussed in the OF use case is about the same idea of which you talked about before, redistributing small flows, maximal bin packing, where you adjust the ECMP hash table using hybrid OF vendor specific extensions again to basically maximize the bandwidth for the other flows. So essentially the large flow using a ECMP link, so then you don't send so much of small flows or other flows using that link, right? You steer them towards the links where there is, there is no large flows. That's the key idea here. So in summary, the final goal is optimal network bandwidth utilization globally across multiple network nodes. That's the end goal. And here the only meaningful way to do this through an SDN, external SDN application again, because it's coordinating across multiple nodes, right? And you could also, rather than using external collector-based techniques, you could use an inline line rate technique to detect the large flow. But then what you would do is you would use IPFix or some technique to kind of communicate the large flow to the global load balancing application. That's another possible strategy. So this work is also going very well in 2 working groups in IET of Ops and IET of I2RS. That is correct. So basically, you have to, instrument each and every node to look at the network utilization, right? Correct. So basically, one way is here you are running, looking at some statistics, correct, continuously to look at what is happening, correct, and then also where the flows are going to learn the flows, correct. So both are happening, and this could potentially be combined with lag also, which I have not indicated. So I think what is very important, I think we decouple the S flow basically, which is used for large flow observation from interface statistics, right? So no matter what, you have to observe interface statistics in all the nodes, because that is the indicator. For example, just going back to this slide. So that is the one and only way to determine that there is poor bandwidth utilization, there is collision, you are oversubscribing, there is no other way, right? But talking of S flow, what you could do is, depending on the topology, you could just have S flow at the edge, right? Because that's where you're recognizing a large flow. And for example, that would correlate with this. I'm doing the inline line rate large flow recognition only in the edges. I don't need to recognize it again and again. Exactly. Both are separate. Yeah. So now deployments where we've seen a lot of interest is interesting use case from MPLS SDN 2013. So this is on-demand global data backup between data centers. So the use cases around globally backing up enterprise data and low-cost data centers, and especially power, cooling, various aspects, where it's much cheaper to maintain OpEx. So there, the idea is to leverage a virtual network and back up the traffic, and this can happen any time of the day. And what we see here is, essentially, lot of large flows, which is essentially backup, right, happening all throughout the day, where such optimizations, especially the global load balancing, comes handy, and it's kind of really a controlled domain by the operator. So it's a single domain, so it's very easily manageable. So it's not unbounded, right? So essentially, the problem spares where we see potential, deployments for large flows around contained, single domains, not across multi-domain. We are not solving those problems because they're way too complex. It needs interaction between multiple SDN controllers, and also way more complex topologies. So yeah, what this leads to is, hey, you have a nice contained, single domain, and contained topology where you can add value by doing WAN bandwidth optimization. That's what it comes to. So the next one is also very interesting. You may have heard of Hadoop and large flows, and there The interesting case, pitched by Rackspace and now adopted many operators is the virtualized Hadoop. So where this is very effective and valuable is in multi-tenant public clouds, right? So where each tenant needs to run Hadoop only for certain hours of the day. I mean, you don't need to run it all the time because you have a website and then post a website and hey, I want to run some analytics on it. How long do I need, right? Probably a few hours a week. So now my data is there in the cloud and I want to just run Hadoop there. And hey, do I need a physical server for such a thing? Then that's where the virtualized Hadoop helps basically. It's all in the form of VMs and it's a shared infrastructure across multiple tenants. And guess what? Hadoop generates large flows, right? And especially during the Hadoop shuffle phase. So then this idea of global data center load balancing, for virtualized Hadoop within a data center gets very attractive, where essentially you're able to bin pack and maximize the bandwidth utilization. And especially operators like Rackspace are really cost sensitive, right? Among how much of infrastructure they want to have. This idea is we feel is really valuable. And other deployments of interest are essentially dynamic data center scheduling across WAN, where operators are looking at dynamic migration of non-performance sensitive VMs. Right? If you have VM where you don't expect premium performance, then move them during certain times of the day to different time zones, across data centers to drive energy efficiency and cost savings. For example, if you look at data centers in West Coast and East Coast and how they charge for electricity is, more like 9 to 5, right? So there is a peak billing rate versus off peak. So now by moving the workload, at a time, around 2 p.m. if you start moving 2 p.m. Pacific, we start moving the workloads, then what happens is you are able to capitalize by running the workload in the East Coast where it's much cheaper. So kind of strategies around that. And here the large flows are indeed created by migrating virtual machines. And the benefit would be substantial WAN bandwidth savings. So the other use cases also we've seen around distributed NFV data centers, where the goal is to cache content closer to the end user. And here again, the dynamic rich media content triggers long-lived large flows across WAN and MAN. And here again, both bandwidth savings for MAN and WAN, that's the value proposition. And additionally, interest or research and education institutions with a lot of large flows and high performance computing infrastructures. Good, so getting to the end, and then now some quick thoughts on what we need to do to integrate this with OpenDaylight. So to make this indeed happen, all these rich real-time SDN applications, we need a policy management framework. Especially there are multiple applications they could generate overlapping rules. DDoS could generate a rule, load balancing could generate a rule. How do you merge and manage all this, right? This is something I think Colin is leading an effort, so I hope we converge on that. That's an important topic. And other gaps are link utilization monitoring, which needs to be done in OpenDaylight. And also we need vendor specific extensions to OpenFlow, lag, ECMP, group table manipulation. And also we would need Yang data models for large flow, this whole slew of applications configuration monitoring. And that the beauty is the Yang data models can be leveraged whether you're doing really an SDN application or a router embedded application. That's the interesting idea of the floating northbound talking to the application or really the network node. And also we're going to submit an OpenDaylight project around this. Feel free to chat with me further on that. And to summarize, so we have seen some interesting real-time SDN analytics applications around DDoS mitigation focused on layer 2-4, then large flow global and local load balancing. And on the future work in SDN analytics, some interesting areas are potentially dynamic service chaining. We talked about static and all those models in the morning. So more around how you dynamically service chain certain flow categories, and something to think about. And this would enable service providers to offer tiered services. And interestingly, on the standardization front, a lot of possibilities, especially when you do the OpenDaylight project. The Yang data models can be standardized in IETF netmod. So that's what I wanted to share. And also, we are demoing these ideas in ONS. Feel free to join us there, ONS. And lastly, I would like to thank all my IETF co-authors on this work. And by any chance, if Shri is here, I would like to thank him. I don't know whether he could join. So, hi Shri, yeah. So, questions?
Has your group studied the use of all optical switches for large flows?
Sure, definitely. I mean, so I think we definitely know those are other ways of solving the problem, but our focus is on IP basically. Yeah. Oh, the question was around all optical and large flow steering, how things happen, optical switching. So my answer was our focus on IP networks, which are deployed by operators today. So kind of, I think the whole value is bin packing. When you talk about load balancing, bin packing in an IP framework, ECMP, standard IP framework, lag ECMP. So of course DDoS is slightly different, interesting angle.
Does hybrid mode need to be standardized, or is it obvious, or?
So I think OpenFlow hybrid is kind of, I think, covered in the ONF, right? But there, what happens is it lets the vendor implement it in their own ways. It's not too prescriptive as I look at it. So yeah, but it's definitely covered in ONF. Anything else? Thank you all for attending. Thank you.